Okay, there is a nice cool breeze today, and hopefully it's not affecting the recording much. It's been really hot the past few days, so it's nice to have this cool breeze. Okay, let's now try to look at the details of how the components are brought together. We already kind of went through some of it. So here is the global picture of land, ocean, atmosphere, and we look at the grids here in the atmosphere, on land, in the ocean, going deep into the ocean with the physical processes alone, including what we talked about in the atmosphere, in the ocean, and on land, like land ice and snow and other details that we talked about. We already know the applications of climate models. There are climate forecasts issued routinely now by numerous forecasting centers across the globe, mostly in North America and Europe, but also now in China, India, Australia, South America, like Brazil. I think Argentina does something. I think South Africa is running something, and so on. Those issues include things like El Nino and NAO and whatever else a particular center may consider predictable and useful for that region or for their country. France, Germany, UK, they all have different things they worry about, and they focus on slightly different things, even though a global model is being run, for example. So there are global models doing global climate forecasts, and many are also resorting to so-called regional climate modeling to produce higher resolution information, as we talked about, for their own country or location, sometimes even down to a city, for example. Ooh, nice breeze, but let me see how bad the sound is. So we looked at this before, couple climate model. There's a coupler which regrids and does the necessary changes needed to go between, let's say, atmosphere, which is integrated first with chemistry and aerosols, produces winds and humidity, precipitation, clouds, etc., and goes into the coupler, is converted into fluxes for the ocean, which runs its biology and sea ice and circulation, and humans can be included with their emissions depending on the time scale, other activities like agriculture, irrigation, deforestation, transportation, urbanization, etc. And land gets fluxes as well, does its biology and land ice and so on. So that's a very simple way to look at it, but coupler is a big deal, and each center tends to have a coupler that does things a little bit differently. So the main natural modes of variability in the climate system, of course, the big monster is El Nino, which happens every 2 to 7 years. I have a bunch of podcasts on El Nino that you can look up. It is centered in the Central Eastern Pacific, and this is basically a nice paper from Wenju Chai and the gang on a review of the pan-tropical climate interactions. Here is the mean state with the trade winds, the upwelling, cold temperatures here, tilted thermocline, Indo-Pacific warm pool, and the ITCZ with the warm temperatures. Gulf of Mexico, of course, is warm, and the Atlantic with its upwelling trade winds and ITCZ, and so on. And there are zonal modes of variability in each of the tropical oceans. Pacific has the El Nino, Indian Ocean dipole over here, Atlantic Nino over here, but these are smaller, so the zonal mode timescales are also smaller, 9 to 12 months here, just a season here, a season there, and so on. So September, October, November, December, January, February peak, June, July, August peak, and so on and so forth. Okay, so looking at the evolution, seasonal evolution here, You are looking at June, July, August of year 0 of the El Nino, September, October, November. You can see how El Nino is developing, but you can also see the connection between the Pacific and Indian Oceans, and the Indian Ocean dipole looks just like that. So there is this continuing never-ending debate about whether Indian Ocean dipole is really independent of El Nino and so on and so forth. But there is also a signature in the Atlantic, so the big monster probably controls the tropical modes of variability. And the big monster really is sitting here, the massive heating associated with 5 meters of rain and the trade winds interacting with that system. And of course, monsoon is a heating system as well. Okay, so El Nino, I won't go through the details, you can look up elsewhere. There are other modes of variability like the North Atlantic mode, which is the oscillation between the Icelandic low and the Azores high, which is at a lower frequency but has higher frequency variations as well. So you can see that based on its phase, it can dramatically change the climate on either side of the Atlantic over the northern US and Canada and Europe and the Mediterranean region. There are other modes. This is the Atlantic multi-decadal oscillation, which means its intrinsic time scale is multi-decades. So it was proposed, and now it is argued that this mode may not be real. It may be just a statistical artifact. These things happen. But what happens is when you simulate long-term variability in a climate model, you want to see if the climate model is able to produce all these modes of variability and how realistic they are. So it's amazing that given just the energy at the top of the atmosphere, most models worth their salt are able to produce all these modes of variability. Of course, they are not perfect, but they are quite useful for doing many of the things. There is of course the Pacific Decadal oscillation, which looks like El Nino but is broader, has a stronger Aleutian low signal, has an Indian Ocean signal, again kind of a east-west pattern there maybe. And there is a debate about whether this is really independent of El Nino or this is a low frequency rectification of El Nino and so on. So for climate models running climate change scenarios, then the question is whether these natural modes of variability impact the trends that we are watching, and it turns out that it does, because El Nino, for example, affects the oceanic heat uptake and the release of the accumulated heat. So there is a mini global warming during El Nino, and if the warming pattern is such that this region remains less warm than this region, then this feedback can go on anthropogenic time scales as well and create things like the warming pause that we talked about. So there is a debate about whether the global warming pattern will look like a El Nino or like a La Nina. And if you look at the warming pattern, which I didn't include but I have talked about it elsewhere, there is a strong wind, sorry about that. There is a strong lack of warming or even a cooling here, and the argument is of course whether it's related to anthropogenic forcing of the Atlantic meridional overturning, which moves heat in this direction. And now there is new paper arguing actually it's the change here of taking away heat from here to the north that is more effective than the Atlantic meridional overturning circulation change here. So whether that's natural or not is again a debate. Regional models typically look like this. This is from a nice review paper from Filippo Giorgi, already a few years old. So he's focusing on the Mediterranean region because he's from Italy. So this is, let's say, a global model. We are running a regional climate model with various ways of increasing grid resolution from the outer domain into the inner domain. There is a so-called buffer zone created because it's the boundary condition relaxation. So if it is a regional model, then you cannot just give it energy at the top of the atmosphere and say run, because it has these open boundaries, which means you have to give it information like winds, temperature, humidity, and pressure at the edges as well. So where those boundary conditions come from and how those boundary conditions affect the interior all depend on how this boundary condition is imposed and what kind of buffer zone is created and so on. But these high resolution models produce more specific information for regions on water, food, energy, ecosystem services like fisheries, agriculture, biodiversity, migration, coastal areas, tourism, and so on. Okay, so a lot of them are being run by each country, and we have already talked about how increasing resolution affects the representation. So going from 500 kilometers to 50 kilometers to 10 kilometer, you can see how the land orography and hence temperature, precipitation, humidity, storms, fronts, everything will be affected by having higher resolution in a regional model configuration, and that's their biggest advantage, despite the disadvantage of having to put in the boundary conditions, and then there are other details that we are not talking about here. And you can see the impact on solutions as well. So this is the observed rainfall pattern of a particular event. GCM basically wipes it out, but the regional climate model is able to capture that kind of a frontal system very well. This is the advantage here. And for the future projections also, now there are attempts to take global GCM projections with various representative concentration pathways, in this case representative concentration pathway 8.5, comparing period of 2070 to 2019 versus 1975 to 2004, and this is what the GCM produces. Using the boundary conditions from this GCM, and RCM adds value to it, giving you more details on how summer precipitation changes. This of course extends into extreme events and so on, which are very useful. How this information can be used, of course, is still something that's up to policymakers, and it's debated whether information that far into the future can be used, and whether model uncertainties are so large that this information is not useful. Just as a passing comment, I will say that in the near term, like for the next decade or two, model uncertainties that I mentioned before tend to dominate the errors or uncertainties in the projections. But when you go to longer term, like 2070 to 2099, it is the scenario uncertainties, the scenarios that are used to create RCPs and now shared socioeconomic pathways. It's those uncertainties in the scenarios that tend to dominate the uncertainties in the projections of, especially precipitation. It's very hard to simulate and project. And integrated assessment models, of course, have gone into creating the RCPs and the SSPs. Okay, there is a coordinated downscaling experiment which takes global projections done under the IPCC model suites like CMIP 5 and CMIP 6. Multiple domains, regional domains like this are created, and higher resolution regional climate models are run for the future for each region. There are debates about whether they really improve the results or not. For example, the coupled IPCC models, CMIP 5, CMIP 6, are coupled models, so they include ocean response, ocean impact, whereas most of the Cordex models, I think all of them, use the sea surface temperature projected temperatures to force the regional atmosphere model. So that begins to lose some of the information. So it is argued that in some regions like the monsoon, where the system is very much strongly coupled between the land, ocean, and the atmosphere, taking coupled projections and downscaling with forced SST force projections actually degrades some of the projections, but that's a detail you have to worry about. But as an introduction to climate modeling, you should remember that when you use outputs like Cordex, you have to be careful. I'm presuming that people who are just interested in introduction to models are not climate modelers, are interested in climate predictions or projections. They are interested in understanding how models are used to make projections and maybe use those projections into your social science, adaptation, mitigation, or whatever else that you may be doing, climate and health, for example. So you should be aware of the product and what are the intrinsic issues that may be associated with the products that you are using. Okay, so let me leave this here for now, and we'll come back and look at some examples of use of the models and how the models are evaluated before I close out this brief series of podcasts on demystifying the models for people who do not want to go through the equations. Okay, I hope they are useful. Okay.